Hello everyone, my name is Anurbhata Guchait and today I'm going to solve some questions from CC5 Sem-3 of the year 2020. I'm going to solve questions live so that you can understand each questions easily, and I'll also try to write each and every steps to make my answer straight and easy. So let's start solving. Apply sandwich theorem to evaluate this limit. Okay, so this can also be done by using L'Hopital rule, which will be much easier. But the question was apply sandwich theorem. Okay, so we're gonna do that. So first of all, um, evaluate the left hand limit and the right hand limit. Okay, so first we're going to evaluate the right hand limit. Okay, now so for the right hand limit, we are taking uh, x. So for the right hand limit, we are taking x in between 0 and pi by 2. Okay, so now in this region, it's sine x greater than x greater than less than tan x. Okay, so it's this thing satisfies in this region. Okay, sine x is less than x less than tan x. Okay, now we are going to divide each of the term by sin x with sin x. So then it will become 1 by x by sin x less than 1 by cos x, where x is in between 0 and pi by 2. Okay, now watch carefully. I divided each term with sin x. Okay, which is where x is inside this region 0 and pi by 2. Now you can see the graph here of sin x. Okay, now for every value between 0 and pi by 2, you can see that the graph is the value of sin x is positive here in this region. So it's positive, so we are dividing each term with a positive term, so the inequalities are not going to change. Okay. So now as we have taken x greater than 0, so limit of x tends to 0 plus of 1, this will be 1 obviously, and limit x tends to 0 plus of 1 by cos x. Now 1 by cos x, that means 1 by cos 0, which will be 1. Okay, so now by sandwich theorem or squeeze theorem, so now this function, limit x tends to this function is 1, and limit x tends to this function is also 1. So then by sandwich theorem, what we can say that limit x tends to 0 plus this function will also be 1. Okay, so limit x tends to 0 plus x by sin x, this will be 1. So the right hand limit, so this is the right hand limit. Now we are going to evaluate the left hand limit. Okay. So let me erase this and this part here. So now, okay, so now for the So now for the left hand limit, what we will take is this, where x is in between minus pi by 2 and 0. So x is in between minus pi by 2 and 0. So now in this region, what happens? Sin x becomes the greater one and tan x becomes the smallest one. Okay. Yes. Okay. Now now we are again dividing each term with sin x. So this will be 1, this will be x by sin x, and this will be 1 by cos x, where x is greater than x less than 0. Okay. So now notice carefully, here the inequality changes. Okay. Why so? Because x in between minus pi by 2 and 0, you can see in the graph that for every values between minus pi by 2 and 0, the value of sin x is negative here. Negative inside this region. That's why, like, we are dividing each term with a negative term, so the inequality will change. Okay. Now same as before, limit x tends to, here it will be 0 minus, as x is less than 0. Okay. 1, this will be 1, and limit x tends to 0 minus of this function cos x, this will also be 1. Okay, so then by sandwich theorem, what do we get? The same limit of this function will also be 1. Of x by sin x, this will be 1. Okay, so now we get both the left and right hand limits. So let me erase this first. Now what we're gonna do is okay, so now the left hand limit, this is of x minus sin x, this is 1, which is also equal to the right hand limit. So we can say that limit of x tends to 0, x by sin x, this is 1. So now limit x tends to 0, sin x by x, this will be 1 by 1, which will be 1. So value of this is 1. Okay, we're going to talk about the sequential criterion of limits. Okay, so let's say this limit, if x is equal to, let's say, number L, which is a rational number. Okay, so this, if and only if for every sequence xn in R minus, so R excluding this point. So this every sequence xn in R A, so this sequence in this converging to C, so this converging to, no, not C, it's A, this point A, converging to C, the sequence f of xn. So the sequence of the functional values of this sequence, they converges to this point L. Okay, so look carefully. It is a if and only if condition. Okay, so if this limit is equal to this, then for every sequence xn in R minus A converging to A, this point, so if a sequence converges to this point A, the fxn, the sequence fxn, they must converge to L. Okay, so now how we're gonna prove this is we're gonna show that we take two sequences which is converging to A. So by this theorem, the sequence of their functional value, they must converge to a single limit. Okay, but they are not gonna converge to a single limit. That's what we're going to show. Okay. So first of all, let us take, let's say un is a sequence of rational numbers in R minus this point. Okay, this point, converging to where? This point A, this point, converging to A. Now we're gonna take another sequence which is Vn. Let Vn be a sequence, is a sequence of irrational points. Okay, so irrational numbers. Irrational numbers in R minus A minus A converging to A. Okay, so we took two sequences in R minus A which is converging to A. Okay, so limit un is equal to A as it is converging to A, and Vn is also converging to A, so it is also equal to limit of Vn. Okay. So now we're gonna see what does this sequence contain. Okay, what does this sequence contain? So it is sequence f of un. So now watch carefully. Un is a sequence of rational numbers. Okay, so now the fx is defined such a way that for every rational values fx is 1 and un is sequence of rational numbers. So what do we get? They are all ones. So now what is f of vn? So what is f of vn? The sequence f of vn contains minus ones, as vn is a sequence of irrational numbers. Okay, so its fx is minus 1 for all irrational values. So f of vn is minus 1, so on. Okay. It's minus 1. So now what we can see, the limit of f of un, it is 1. Okay, as it contains all ones. Okay, and limit f of vn, it is minus 1. So now what do we get? We get two sequences un and vn. They are from here r minus a, both are from r minus a, and they are converging to a. Okay, so now by sequential criterion they should converge to a single limit. The f of un and f of vn, they should converge to a single limit, but they are converging to different limits. So they are not equal. So then we are gonna write that. Okay. So you can just erase it. So now we get, what do we get? un and vn, they both converges, they both converge to a. Okay, now but f of un and f of vn, they doesn't converge to a single limit. Almost to a, this is same limit. Okay, so same limit. So then by sequential criterion this doesn't exist. So now it is a very common question. Okay. So in this kind of question, what we need to do is, first we gonna, so if you see a question like, say, evaluate this limit, and there's a function here and a function which is the power of this function. Okay, so there are two functions, which is the power here and which is the main function. So in this kind of limits, what we're gonna do is we're gonna take this function as y. So let's start solving actually. So we're gonna take, let y is equal to 1 plus tan x and 1 plus sin x 1 by sin x. Okay, this is the key point here. Okay, so now what we're gonna do here, we're gonna take log on both sides. So say log y is equal to 1 by sin x log of 1 plus tan x by 1 plus sin x. Okay, now we're going to take the limit. Okay, now we're going to take the limit. So limit x tends to 0 plus log of y is log of limit x tends to 0 plus 1 by it's log of this and sin x. Okay, so now observe it very carefully. So if we put 0 here and here, it will be tan 0 will be 0, sin 0 will be 0, it will be log of 1 which is 0. So this part will be 0 and this part will be sin 0 will also be 0. Okay, so in this case we're gonna use the L'Hopital method. Okay. So what we're gonna do here is actually we're gonna derivate this part and this part. Okay. So limit x tends to 0. So now we get this. Okay, so now we're gonna put 0. Now we're gonna calculate the limit. Let's see what we get. It's 1 plus sin x by 1 by tan x. Sin x will be 0, tan x will be 0. So it will be 1. Okay. So now sec square x, which is 1 by cos square x, which will be 1. So it will be 1 and it will also be 1 and it will be 1 plus sin x. This will be 0, which will be 1. So this part will be 1 and minus cos x which will also be 1 and 1 plus tan x which will also be 1. So it will be 1 minus 1 which will be 0 and it will be 1. So 0 by 1 and this part was and this part is 0. No, this part is 1 actually. So 0 into 1 which is 0. So now what do we get? And it is 1. So 0 by 1 which will be 0. Okay, so now what do we get is limit of y and this. Okay. So what do we okay, this we take log outside of this limit and it becomes limit x tends to 0 y log outside. Okay, so log of this thing, this is 0, which is log of 1. So log of this is equal to log of 1. So this will be same as 1. So limit x tends to 0 plus y, which will be equal to 1, and y was the whole thing. So limit of this thing will be 1. Okay. This is the question of 3b. If closed 0 to 1 to R be continuous on 0 1 and if assumes only rational values. Okay, so if is defined only for rational values, it is undefined for irrational values. Okay, so if assumes only rational values. Now if f of half is half, then prove that fx equal to half for all x in its domain actually. Okay, so we need to show that fx is a constant function which is half, and the given is f of half is half. So now let's talk about the approach. So how we are going to approach? Okay, let's say this is 0, this is 1, and this is half. So f of half is half, so it is 1 by 2 here. Okay, it is 1 by 2 here. Now we don't actually know what is f0, what is f of 1, or the other values except this one. This one is half. Okay, so now how we're going to approach this is, first we are going to take a point from 0 to open half, which is not half but less than half. Okay, but or before the half. Okay, so open half, let's say x1. We take x1 from 0, from closed 0 to half. So okay, so x1 belongs to closed 0 to half, and we're gonna show that x1 is equal to half. No, f of x1 is equal to half. Okay, so we're gonna show that f of x1 is equal to half. Okay, and then by same method we're gonna show that x1, now x2 taken from this interval closed 1 to open half, as f of half is already given, f of half is half. So then by similar method we're going to show that x2, which was taken from open half to 1, f of x2 which is equal to half. So the whole thing becomes half. So we're going to show that first. This is how we're going to approach this question. Okay. So let me draw it here actually. This half 0 1. Okay, we're taking x from here, x1, and x2 from here. So now we're going to set okay, so now so let x1 belongs to closed 0 to half. Okay, closed 0 to half. Closed 0 to half. So now two cases arise. Okay, so either let's say f of x1 is equal to half, or f of x1 is not equal to half. Okay, so f of x1 is equal to half or no, or not equal to half. So if f of x1 is half, okay, we get what we have wanted. Okay, so we get what we have wanted. And, but if f of x1 is not equal to half, then what we're going to do? So if f of x1 is not equal to half, then what's going to happen? Okay. Okay. So now, let's say so let so as this 2 is not equal to half, and what is if so this equals to f of x1 is not equal to f of half, as f of half is half. So now f of x1 is not equal to f of half, so as they're unequal, there must be a real number between them. Okay, so let q, or let's say let there exist a irrational number q belongs to these 2 points. So open f of x1, f of half. Okay, so q belongs to these 2 points, this interval actually. So q belongs to this interval. Okay, so q belongs to this interval. Now q belongs to this, and f is continuous, and q belongs to this, and they're also unequal. Then by intermediate value property, which is IVP in short form, we get by intermediate value property, we get f of q equals to c, or more precisely, there exists a c, let's say c1 belongs to x1 comma half, such that f of c is equal to q. Okay, but this cannot happen. Okay, this thing cannot happen, as it is contradicting the fact that f assumes only rational values, but q is irrational here. Okay, so this thing is imaginary, this thing cannot happen actually. So which is a contradiction, which is a contradiction. Okay. So now what do we get? So our assumption is wrong. So this was our assumption. Okay, this is wrong. So our assumption is wrong. Our assumption is wrong. So this was wrong. Therefore, f of x1 is equal to half. Okay, f of x1 is equal to half. So what do we get? F of x1 is half f of x1 is half for all x1 belongs to close to 0 to. Okay, so now similarly we can show that. So let's say, so we will write that similarly we can show that. So similarly we can show that f of x2 is equal to half for all x2 belongs to open half to 1. All clear now? Okay, so this is half. Every value between them is half. Every value between 0 and 1, also 1, is half, and this is also half. So now write, and f of half is half. So what do we get? So f of x1 is half, x1 is 0 to half, half to 1 is also half, and f of half is also half. So fx is half. Fx is half. Okay. Fx is half for all x belongs to therefore f of x is equal to half for all x belongs to 0 to 1. Proved. Question number 4, which is so let's see, the image of a closed and bounded interval under a real valued continuous function is a closed and bounded interval. Okay, so what is a image set, or what is the image of a function? Okay, so let me tell that first. So let's say there's a function f which is defined from a b to, let's say anything mn. Okay, let's say, so, or it's not take there. Okay, so there's a function f and it is defined here in this set, so which is, this is actually f of x. Okay, so say a becomes f of a here, b becomes f of b here. Okay, so this is called the image of f. This is the image. Okay, so the actual question, so the actual theorem is say if, okay, f is continuous on a closed and bounded interval, let's say a comma b. F is continuous on a closed and bounded interval a comma b. Okay, so now then prove that f is bounded and also closed, obviously. Okay. So now we're going to solve this, which is prove that there exists a point A in between 0 and pi by 2 such that A minus cos A, this holds. Okay, so now what we're going to do here is we're going to take a function first. So let us consider a function which is if x minus cos x, okay, where x belongs to this region 0 comma pi by 2. Okay, now what we will show that this, like, there exists a point here, it will be A, so there exists a point A such that this thing will be 0. Okay, so let's find the value of f0 first. F0, what will be the value of f0? X of cos 0, which will be which will be minus 1 actually. Minus 1. Now what will be the value of f of pi by 2? This will be pi by 2 minus cos of pi by 2. Okay, this will be pi by 2 minus cos pi by 2, which will be this will be 0, so this will be pi by 2. Okay, so what do we get? f0 is not equal to f of pi by 2. Okay, and if is continuous, and if is continuous on this interval 0 to pi by 2, what do we get? If is continuous on this interval and the function value of end points are unequal. Okay, or it's not actually unequal, it is also unequal and are of opposite signs. Okay, so what do we get? f0 and f0 and f of pi by 2 are of opposite signs. They are of opposite signs. Then let me erase this one. So this was our fx. Fx equal to x of x minus cos x, where x belongs to 0 to pi by 2. Okay, so now what we can say that by Bolzano's theorem, we can say that there exists a point A belongs to 0 to pi by 2 0 pi by 2 such that f of a is equal to 0. This implies a of minus cos a is equal to 0. This implies a is equal to cos a. Okay, so proved. Okay, so this is the next question. Give an example of a function which is continuous on R, attains its supremum but is not bounded below. Okay, so we need to find a function which has actually a maximum value but doesn't have a minimum value, as it will be not bounded below. So let us take the function minus x square all over the interval R. Okay, so what will be the graph of this function? So, and this is 0. Okay, so this is x, this is fx. So now minus x square, it will be actually like this. It's like opposite of x square. So this is y equal to minus x square. Okay, so now what we can see here is the maximum value of this function is this, fx equal to 0 at the point 0. So it will be rather x f of 0 is equal to 0. Okay, but here as x tends to minus infinity, like here as x tends to minus infinity, if x tends to where minus infinity here, and as x tends to infinity, if x tends to infinity. So what we can write here now is, so this function fx is continuous on R, okay, as it is a polynomial, as if x is a polynomial. Okay, and the maximum value of if x is 0 at x equal to 0. So the supremum of if x, where x belongs to R, what will be the supremum? It is 0. Okay. So this is supremum, and it is attained as f of 0 is equal to 0. So it is attained. Okay, and now for x tends to minus infinity, for x tends to minus infinity, if x tends to minus infinity. Okay, so so what, as x tends to infinity, minus infinity, here in this region, we can see that, like, if x is downwards, okay, so if x tends to minus infinity, and here in this region x tends to infinity, if x is if x is tending to also minus infinity, as it is also downwards. Okay, so, and for x tends to infinity, if x is tending to also minus infinity. Okay, so it is not bounded below. As we don't get a infimum of this function, so it's not bounded below.